We've looked at stepper motors before, but today in the workshop we'll be working with a big stepper motor. We'll see how to read stepper specifications and choose a driver for your motor. We'll also use an Arduino to control everything. We're taking some big steps today, so welcome to the workshop. Hello and welcome to the workshop, and today we're going to be working with stepper motors again. Now, we've looked at stepper motors before. We did an entire video about stepper motors, and in that video I explained how a stepper motor differs from the other types of motors that we've used in our projects, what the different types of coil windings are, your bipolar and unipolar stepper motor windings, how to drive stepper motors using dedicated driver modules and also using H-bridges, and concepts like microstepping. Well, we've covered all that, so that's not what we're going to cover today. Today what we're going to cover is what we need to do in order to drive a large stepper motor. Now, this is a very big stepper motor. This is a NEMA 23 size stepper motor that consumes a good amount of current, 4.2 amperes, in order to get the full capacity out of it, and it's a very powerful motor. Now, this motor is too powerful for the modules and H-bridges that we've looked at before. So we've got two choices. One choice would be to build our own drivers out of MOSFETs, which is not what we're going to do today. Instead, what we're going to do is we're going to use a controller. Now, this is an industrial size stepper motor controller, and there are a variety of these out there. What we're going to learn today is how to read the specs on our stepper motor in order to select a controller for it, and then we're going to see how we can hook this up to an Arduino and control the stepper motor. So we're going to start off first by learning how to read the specifications on our stepper motor to determine what type of a driver module we need to select in order to use it. So let's go take a look at that right now. Now, we've already covered the basic specifications of stepper motors in my previous video, so if you need an update, please go and see that. What I want to show you is in the real world how you would read the specifications on a stepper. Now, this is the stepper motor that we're going to be using today, so let's take a look at some of the specs that are listed on the Stepper Online website. Now, here are the electrical specifications. Now, this is a bipolar stepper motor, and in the previous video we covered the difference between bipolar and unipolar steppers. It has a step angle of 1.8 degrees, meaning on one full step the motor shaft will move 1.8 degrees, and of course we can microstep this to get finer resolution. By calculating that, you can see that it would take 200 steps for this to make a full rotation. Now, here's the holding torque, specified both in Newton meters and in ounce inches. And now here is probably the most important specification in the entire electrical specs, and that's the current per phase, and that's 4.2 amperes. Now, this will be where it gives its maximum torque. Also, keep in mind that if you're going to microstep this, and you likely are using this controller, then you will actually have to double that current requirement when choosing a power supply, because this is per phase, so it means each one of the coils could be at 4.2 amperes simultaneously. Now, here, conversely, is the least important specification here. Now, the voltage, 3.78 volts. What in the world is that all about? As I said earlier, I am going to be driving this with my bench power supply, and I'm planning on using 24 volts, and some people may be using 60 volts or 48 volts to power this motor. Why does it say 3.78? Well, this is the reason. The phase resistance, this is the electrical resistance of each of the coils, and it's 0.9 ohms. Well, if you're good at math, try multiplying 4.2 by 0.9. Guess what you're going to get as a result? This is just simply a calculated voltage. This has nothing to do with the maximum voltage that the stepper motor can be operated at, and I'll show you another example of that in a few seconds. Now, this is the inductance, which is a very useful thing to know if you're actually designing the stepper motor driver, or if you're trying to determine what the maximum frequency you could drive the motor is at. Then after that, we get into some physical specifications. specifications. Now this is a NEMA 23 size motor, so these specs are all fairly consistent. And the connections, which is a very important thing, of course, to know, because this is coil A plus and A minus and B plus and B minus, and this gives you the color codes of those wires. Now this also links out to a couple of spec sheets. Let's go take a look at those, because they have some information as well. Plus, you may not be going to a website for your stepper motor. You may indeed just get a couple of spec sheets included with the motor. Now here's the first one, which goes over most of the physical specifications for the motor, and again the electrical specs, which are as we have seen before. And notice they put the amps and the resistance at the very top. Notice also, if you're going down through here, you won't even find the voltage listed, because again, that's just a calculation based upon these two. And these are all the same specifications we've seen before, other than things like step accuracy and inertia, etc., and the weight of the motor itself. Now the other diagram they have is actually very interesting. It's a torque diagram. Now this is the pull-out torque, and notice that this is rated at 36 volts, despite the fact that this motor was only specified at under 4 volts. This is another example of how little the voltage reading actually means in the stepper motor specs. And this is at 36 volts at 4.2 amperes, and notice it is half steps. So in other words, 2 coils will have been activated at the same time in this configuration. Now let's go down to this chart and take a look at it. Now this is the pull-out torque, and notice that the torque decreases as the speed increases on the stepper motor. Now they start this off at 60 RPM, which is 1 revolution per second. And notice that it says you need 400 pulses per second. Well, remember, it takes 200 pulses in full step mode to turn the motor, so it would take 400 pulses in half step. So this relates both the frequency and pulses and the speed in RPM for you, which you can also, of course, just calculate mathematically. And again, as you can see, the torque will decrease as the stepper motor is moving faster. And so this is basically how you read the specifications when you are selecting a stepper motor. Alright, now here's the stepper motor that I'm going to be using, and as you can see, this thing is quite the beast. It's NEMA 23 size, so you can see it's got a very large D output shaft over here, and the NEMA 23 standard mount on it. This is a bipolar stepper motor. Its specs are it has a stall current of 4.2 amperes, and it has a stall torque of 425 ounce-inches, which is quite a lot of torque. That's also the same as 3 Newton meters, if that means more to you. And as a bipolar motor, it's got 4 output leads, which just come out to bare wire over here. And I've got a multimeter over here so we can measure the coil resistance, and as you'll see, it's quite low. And yeah, 0.9 of an ohm is what I'm reading over there. So there's very low coil resistance on this. Now, its nominal voltage is rated at 3.78 volts. Of course, as we just saw, that voltage rating is just basically a mathematical calculation of the stall current and the resistance of the coils. So this is the big beast that we're going to be working with today. Alright, now that we understand a bit more about reading stepper motor specifications, and we've also looked at the stepper motor I'm using today, it's time to focus our attention on the driver. Now this is the driver module I'm going to be using, but I want to make it clear that you don't need to use the identical module that I'm using. I have based my selection of the module on the current requirements of my stepper motor, and that's what you should do as well. And there are a variety of modules that look just like this one, and that can work in the same Arduino circuitry. They're hooked up the same, and they can use the same code. The only difference is their voltage and their current ratings. As well, you're going to see there are some dip switches on the side of the driver, and the selections you make for your particular motor and driver combination may be different than the ones I'm using, but otherwise you can use basically any one of these drivers. I got this one on Amazon. You can get them on eBay, at electronic and electrical supply stores as well. So let's take a closer look at the driver right now. Now here's the motor driver that I'm going to be using today. As I said, this is typical of most Microstepper motor drivers. Now they'll have connectors on the side, and these connectors at the top over here where it says power and fault is where you're actually going to put the input connector from the Arduino. So we're going to control both the direction and the pulses of the stepper motor by feeding signals into here, and they come in the dir minus, dir plus, pulse minus, pulse plus, enable minus, enable plus. You'll find when we do the wiring it's going to be a little bit different than what you expect. We're actually going to be using a common 5 volt and not a common ground for these. Now down at the bottom you've got the connections that go to the motor itself. So one coil, the A plus and A minus, and the other coil, the B plus and the B minus. And at the bottom over here we have the power supply connection. Now this particular one will work on both AC or DC. So if you're using DC, you put the positive here and the negative one over here. AC, of course, you can connect either wire anyway. And this one has a range, this particular one, of 18 to 80 volts AC or 24 to 110 volts DC. This is actually about the same range. If you multiply by 1.414, which is what you do when you have a full wave rectifier, you'll find that you're pretty well in the 25 to 113 volt DC range by supplying AC. Now these connectors are kind of nice. They are screw connectors, but they also just come off like this so that you can connect your wires externally and then mount everything onto here just by plugging it in. And that's very handy because, as you can see, this is a pretty big beast over here. Now on the side they have a table, and the table tells you how to set it up for things like current limiting, and so it gives you the different currents that you can set it up for, and also for microstepping, for the number of pulses per revolution. And this is the table that determines that over here. And you set all of this up on the side over here on a dip switch. They have a switch on the side that you can use to set everything up. Now this is quite the beast. It's in a metal case, and on the back you can see it's got a heat sink that has a fan as well on it. So this is expecting to dissipate quite a bit of heat and should be mounted in an area where that heat can vent. So there you have it, the motor driver that we're going to be using in today's big stepper motor experiments. So we've seen the motor, we've seen the driver, it's time to hook everything up. Now there's one other component that we haven't looked at yet, and that is the power supply. Now I'm going to be using the power supply on my other workbench today because it's a variable supply and it can supply up to 30 volts at 5 amperes, and that should be sufficient to be able to drive the motor. And in my case I'm driving my motor at 24 volts. Now remember, your power supply is going to be determined by your driver and your motor, and so you may be using a different voltage and a different current, and that's fine as long as your power supply is capable of supplying the driver. You can also note that many drivers, including the one I just showed you, have a built-in rectifier and can accept AC voltage as well as DC voltage, so you could use an AC transformer instead of a DC power supply if you have that type of drivers. Now the Arduino will be powered from your computer's USB power supply, so it isn't affected by the power supply in the driver. So let's take a look now at how we hook up our motor and our driver and our power supply to our Arduino. Now for our first experiment, you're going to need, of course, your motor driver and your stepper motor, as well as an Arduino. I'm using an Arduino Uno here. In addition, you're going to want a push-button switch, a pull-up resistor for the push-button switch. I used a 10K resistor, and a potentiometer. Any linear pot of a value of 5K or above will suffice. I'm using a 10K pot. Let's start by connecting the motor driver to the Arduino. Pin 6 from the Arduino goes to the dir minus connection on the stepper motor driver. Pin 7 from the Arduino goes to the PUL minus connection on the motor driver. Both the dir plus and PUL plus connections on the motor driver are connected to the 5 volt output of the Arduino. One side of the push button switch is connected to pin 2 of the Arduino. A 10K resistor is also made from this connection up to the 5 volts on the Arduino. The other side of the push button switch is connected to the Arduino's ground. One side of the potentiometer is connected to the Arduino's ground, the other side to the 5 volts from the Arduino, and the wiper of the potentiometer is connected to analog input A0. And at last, make your connections to the stepper motor and the power supply. Your stepper motor should be connected looking at your motor specifications, with one coil going to the B positive and B negative, and the other coil going to the A positive and A negative. You will also need a power supply whose specifications depend upon your motor driver and to some degree your stepper motor. Now I'm using a 24 volt power supply, and it's a DC supply, so I'm observing polarity as I connect it to my motor driver. My motor driver will also accept an AC input, but some won't. Again, look at the specs of your motor driver and your motor to determine the requirements for your power supply. And now that this is all hooked up, let's take a look at a simple sketch we can use to test everything out. Now the first sketch that we're going to run on the Arduino is going to be very simple. All we're going to do is we're going to pick up the movement of the potentiometer and use it to control the speed of the stepper motor. Now we are not going to be using any libraries in this sketch. We're just going to be pulsing the motor directly through the Arduino code. But what this sketch will do is it will give you a good idea of how easy it is to work with the motor controller and how the different control signals work. So let's go take a look at that sketch right now. Now here's the sketch that we're going to use to test our large stepper motor. Now it's a pretty simple sketch and it doesn't require any libraries. We're going to start off by defining a number of pins, and so a reverse switch is where we've connected the switch, and that's pin number 2. Now of course I've used a push button here, but bear in mind this could easily be a limit switch, and you could even have more than one of them in parallel. So for example, if you're trying to move the motor between two extremes, you could put a switch on each end. And also this does not of course have to be a mechanical switch. In fact, it would probably be better to be an electronic switch such as a Hall effect sensor or an optical switch. So just some food for thought over there. Now, this variable defines where we send the pulse pin. This is the PUL input on our motor driver. So we set that to pin 7, and pin 6 we've set to the driver for the DIR pin. And we have our potentiometer, and it's connected to pin analog A0. Now a couple of variables. Now PD is the pulse delay period. Now this is the inverse of the frequency, and we're going to set it to an initial value of 500. And we also define a Boolean, and we call it setDir, and we initially set it as low. Now this is going to set the direction, and so toggling this will reverse the motor. Now we have an interrupt handler, which I'm calling rev motor, and all it does is it takes this setDir variable and inverts it. So whatever setDir is, the inverse will come out. If it's low going in, it's high going out, or vice versa. Okay, now down to our setup. The setup is very simple. We set the pin modes for the 2 pins that we've defined to connect to the motor controller as outputs, and we also attach the interrupt to the reverse switch, the switch that we've defined on pin 2. Now this is the correct format of attaching an interrupt. You use the digital pin to interrupt function and give it the pin number as opposed to the interrupt number, which you could also have inserted over here. And then when that interrupt is triggered, we call rev motor, and we trigger that interrupt on a falling pulse. Now remember, that line is held high, so if the push button is depressed, the line will go low, and that will be a falling condition, and that will trigger the interrupt, which in turn will call this interrupt handler over here. Now down into the loop, and again this is quite simple. We have to determine the pulse duration first, and we do that by reading the speed using analog read. Remember, this is connected to pin A0, and we map that using the map command, or the map function, excuse me, from a value of 0 to 1023, because that's what the input value is going to be, and we map it to a value of 2000 to 50. Now notice we're going in the opposite direction here. This is so the speed increases as we go clockwise, because again the pulse duration is the inverse of the frequency, so the larger this number is, the slower the motor is going to spin. Next, we write out our direction to the set with the set dir value to the driver dir pin. So whatever that value happens to be, it'll set the direction of the motor. And then over here, we're going to send the pulse pin high. We're going to delay it for the period of the pulse width, or the pulse delay. And then we're going to send it low and delay it for the same period. So what we're doing with these four statements is essentially creating a pulse. And then this is a loop. We just continue to repeat this over and over again. So quite a simple sketch. Let's take a look at it in action right now. So here's the test setup that I've got to test my large stepper motor. Now, because of the amount of torque that this motor gives out, I didn't want to just leave it on the workbench because it could be a bit of a danger, especially as you can see I'm using a miniature vice grip as my indicator of the motor shaft position. So I put the entire combination here into my bench vise. And over here, of course, you can see the stepper driver. I've got it connected to the stepper motor, plus to a power supply that you can't see that's going to be supplying 24 volts to it. And down here are my connections to the Arduino. At the back, I've got the potentiometer I'm going to use for controlling the motor speed, and the switch I'm going to use to reverse the motor. And remember, this switch could also be another type of switch, an optical switch or a Hall effect switch, and you could use it at the end of the travel of the motor or whatever the motor is driving to make the motor go in the other direction. You could even put two of them in parallel if you wanted to. Now, I haven't done any debouncing on this switch, so occasionally when I press it, it's going to think it's being pressed twice, but if you used an optical or electronic switch, you wouldn't have that problem. So what I'm going to do right now is fire the power up, and as you can see, my motor's rotating, and as I move the pot, I can get it faster. Now right now, by the way, I have this set so that one revolution is 800 pulses using the dip switches on the side here. And of course, as you microstep this differently, the speed will change. Now I'm going to move it up a bit more. Now there it's going pretty fast. That's pretty scary actually, watching that vice grip go around. I hope it holds on. Let's turn it down to a slower speed now. Okay, now let's hit the switch. You can see the debouncing in effect. There it goes in reverse. Reverse. Reverse again. So as you can see, aside from perhaps a few debouncing considerations, this seems to work pretty well. So as you can see, it's pretty easy to use a stepper motor with the Arduino and some simple code, but we can improve our code by using a library. Now the AccelStepper library is one that we've used before. It is a very, very common library for stepper motors, and with this library you can achieve some very precise control of your stepper. So we're going to do another demonstration using AccelStepper. Now keep in mind that since this is such a common library, there are a lot of sketches out there that make use of this library, and so now, armed with the information you have, you can take those sketches and use them with your large servo motor. So let's take a look at AccelStepper now. Now in my original video on stepper motors, I went through the AccelStepper motor library in some detail, so I won't repeat myself over here. If you were following those videos, you probably already have the AccelStepper library installed in your Arduino IDE, but if you don't, you'll need to go through the library manager and do it. So go down under Sketch to include Library, and then go to Manage Libraries. Once the library manager is open, just filter your search by typing AccelStepper. And here is the AccelStepper. Now I've already got mine installed, but if yours is not installed, when you highlight it with the mouse, an install button will appear like it does with this library I don't have installed. So just hit the install button on AccelStepper, and that will install the library for you. Once it's installed, you can use some of the built-in example sketches in order to run your motor controller. All you need to do is change the initial line in the sketch actually. So let me show you. I'll go down and open examples, and then scroll down to examples from custom libraries, and you see AccelStepper. And there are a number of different examples you can try. There's one over here called Bounce. Let's just take a look at that one for a second. This is a pretty simple one. This one essentially sends the motors from one limit to another, and it accelerates and decelerates as well, so that's actually kind of a nice feature. Now, the only thing you need to do is at the beginning over here is you need to define the object stepper in a different fashion. So what I would do is I would just remark that one out, give myself another line here. And this is the fashion that you want to do it. So what you're telling AccelStepper to do is create an object called stepper. The mode over here is number 1. This indicates the way that it communicates with the stepper, and that's the correct mode for our modules. And 7 and 6 are where we have connected our pulses and our dir connections. So just do it in that particular format for any of these examples, and it'll work fine. So let's go and take a look at the bounce sketch right now running on our stepper motor example. So I've loaded the bounce example from AccelStepper up to my Arduino. Now you can try some of the other examples as well. All you have to do is remember when you're defining the stepper object to use the syntax that I showed you, and you can change any of the existing examples. You can, of course, also use other code that uses AccelStepper using one of these driver modules. So all that remains to do is to put some power on. And we've got it right at the end. Now AccelStepper, what it does is it accelerates the speed, and then it rotates, and then it decelerates and comes to a stop, and then reverses and does the whole thing all over again. And there you go. Now one thing you probably can't hear, because I think my noise reduction technology is muting it for you, but on the stepper driver the fan does come on every time that I power it up. And I haven't really felt any heat off of this. I ran this the other day for a few hours. There was a bit of warmth on the stepper motor. Of course, I'm not driving it at anywhere near its full capacity, its full torque. So what I'm going to do now is I'm still stepping this at 800 pulses per revolution. I'm going to turn the power off for a moment, and I'm going to use the dip switch on the side. Now they have a diagram here that tells you the microstepping as well as the current setup, and so you need to set this up correctly. Make sure not to exceed the current of your stepper. But I'm going to press this one down, and that should cause it to only use 400 pulses in order to do a revolution. So let's turn it back on. And it is moving faster, definitely. And so using microstepping and the speed controls in AccelStepper or whatever sketch you're using, you can control both the speed of your motor and to some degree its torque, because different microstepping modes will give you more torque. Okay, well that about wraps it up for today's video. I hope that you enjoyed it, and I hope that you're now inspired to start building things with really big stepper motors. But before you run out and start building all of those things, I just need to caution you that big stepper motors, like all other big motors, can exert a great deal of torque, and therefore can be dangerous if you have your hands or other appendages in the wrong places when you're working with them. So do be careful when working with these motors. Now, if you need some more information about driving big stepper motors with the Arduino, you can check out the article on the DronebotWorkshop.com website, and you'll find a link to that article right below this video. While you're on the website, please consider subscribing to the newsletter. It's my way of staying in touch and of finding out what content you would like me to create for you in terms of both videos and articles. And if you haven't yet, please subscribe to the YouTube channel. I'd very much love to have you as one of my subscribers. So until the next time we meet, take care of yourself, be careful with those big stepper motors, and we'll see you soon again here in the DroneBot Workshop. Goodbye for now.